All right, welcome back to part 2 of the review. This video is going to cover from the Stacy Q question about driving a car all the way to the end of the video, so stick with us. Stacy Q is driving a car around a 4,200 foot long racetrack. The race is over when she completes one entire lap. It's a very short race. The distance she travels can be found using the function d of t is 5t squared plus 10t, where t is the time passed in seconds, and d is the total distance traveled in feet. So I like this line. It tells you exactly what the function means. So d of t is saying distance in terms of time. What is the average speed of the car during the first 10 seconds of the race? Average speed, just like before, needs 2 times. First 10 seconds is telling you what those times are. Time 1 is going to be 0. Time 2 is going to be 10. All right, the distance at 0. So instead of writing out some words, I'm just going to write d of 0. The distance at time 0 is 0. The distance at time 10, we plug into the function. So we're going to do 5 times 10 squared plus 10 times 10. So every time you see a 10 in parentheses, that's where a t was in the original. And we can do this. This is 500 plus 100 equals 600. So we're going to do a difference quotient. We're going to do the function's called d. So our difference quotient, we use the name of the function. So I'm going to do d of 10 minus d of 0 over 10 minus 0. This is the difference quotient. It gives us average speed. So it's going to be 600 minus 0 over 10 minus 0. And that's going to be 60. What are the units on this? You can't have a question without units. So distance is in feet. The 10 was in seconds. Right, I'm going back to this original statement where they tell us what all the units are. So this is going to be 60 feet per second. Part B asked, how long does it take for Stacy Q to complete the race? Well, they told us about the race. It's a 4,200 foot track, and it's over when she completes one lap. So the total distance when she completes the race will be 4,200, and that's going to equal the original function, which was 5t squared plus 10t. I know that this test is not a factoring test, but factoring has to be in your arsenal. If we give you factoring questions, this will probably be as hard as they get, and they probably wouldn't be quite this tricky. Not that this is necessarily tricky. First thing to do with factoring is you need to get it equal to 0. So we're going to say, all right, 0 is 5 t squared plus 10t minus 4,200. And then we're going to divide everything by 5, and you have to do everything by 5, including the 0, by the way. Everything is divided by 5. 0 divided by 5 is 0. We're going to get t squared plus 2t, and 4,200 divided by 5, well, 4,200 divided by 10 would be 420, so this is going to be minus 840. Doing a little bit of scratch work, I noticed that 840 divided by 30 is 28, and that 30 and 28 are 2 units apart, so that's a clue that those should probably be my factors when I write out the linear factors here. So the linear factors for this become t minus 28 times t plus 30. The signs are chosen so that when we multiply everything back together, we'll get a positive 2t. And that's going to give me 2 solutions, t equals 28, or t equals minus 30. And remember, we're trying to solve for what time she finishes the race, so unless you think she's a time traveler and she can finish the race in negative 30 seconds, she finished the race 30 seconds before she began, then the answer here is 28 seconds. That is, she finishes the race at 28 seconds. Or maybe instead of at, you might say after 28 seconds. All right. The reason they asked us for that is really because of this next question. What is the approximate instantaneous speed of the car the moment it crosses the finish line? So there's two clues here about what we're doing. They use the word instantaneous, and they're asking about the moment it crosses the finish line. Remember that our moment is 0.001 seconds. That's what we mean by a moment. So we're going to have two times. We're going to have time 1 and time 2. We don't know how to do an instantaneous speed without 2 points. That's the whole deal with the approximation. So our time 2 is going to be exactly when she crosses the finish line, 28 seconds. Our time 1 is going to be a little bit before. In fact, it's going to be so close, it's going to be 27.999 because you did 28 minus our 0.001 seconds. So we're going to plug everything in. I know that f of t2, or sorry, we'll just write f of 28. F of 28 is 4,200 because that's a complete race. Right? We don't need to plug that back in. We did it in the previous problem. And I need to plug in 27.999 into the function. We're going to pause while I do that. All right, I've plugged 27.998 into the function. I'm about to hit enter. I'm going to show you how to finish this calculation entirely on your calculator, and I'm going to show you what I'd like to see written down. So we've got this number in our calculator. What we're going to do is 4,200 minus that answer. Boom. And then we're going to divide it by, divide it by 0.001. So, in theory at least, our average speed is 579.98 feet per second. Notice that, if you just looked at the work on this page, once I clear the calculator away, how the heck did this person get from here to there? Question mark, question mark, question mark, question mark. There's no way to know. So here's what I'd like to see on the page. You need to write me what f of 27.999 was, which, looking at the calculator, it was 4199.42002. And then you need to show me the difference quotient that you use. So we did 4,200 minus 4199.42002 divided by 28 minus 27.999. This equals that. When I first got this number, it seemed a little big to me, right? Like, oh my god, she's going 578? That's really, really fast. Then I remembered it was in feet per second. So, that's a lot of feet. She's a race car driver, but it's not like she's going 500 miles an hour. She's not a jet. It does seem like a reasonable answer. Remember, this is her speed at the moment she crosses the finish line, where she's probably trying to go the fastest to kind of break through this problem. So in contrast to the last two problems, this problem's a math problem. There's no story involved, there's no units involved. It just says, find the average rate of change, and it gives you two x values. So this, you can go straight to the difference quotient. x1 is 5, x2 is 11. You're going to need to know what f of 5 is, and you need to know what f of 11 is. I'm switching to function notation because of this y, just replace this y with f of x to match our difference quotient. So when you plug in 5, it's 2 times 5 squared plus 5 times 5 minus 1. So that's 50 plus 25 minus 1, which is 74. And when you plug in 11 squared, that's 2 times 11 squared plus 5 times 11 minus 1. That's going to be 2 times 121 plus 55 minus 1. So that's 242, sorry. 242 plus 54. So that's going to be 296. So now I've got my values. I got 5, 11, 296, and 74. It looks like the function is increasing over time, so let's just plug this in the difference quotient. 296 minus 74 over 11 minus 5. When you put this in your calculator, if you want to just put it all in one go, this expression that is, then you need to put parentheses around the whole top and the whole bottom. You may not need some of these, but just put them in there to be safe. Tell the calculator what you need. And so when we plug it all in, we're going to get 37. And so there's no units in this problem, so this is just the answer. This is the average rate of change. So we can do this problem entirely without a graph. I think we ask about the graphical interpretation very, very soon. All right, this problem is a little more conceptual. It's something you have to know. It's the difference in calculating average rate of change and approximate instantaneous rate of change. So average rate of change and approximate instantaneous rate of change actually have a lot of similarities. This does explain the differences, but I'm going to start by explaining the similarities. Both of these use a difference quotient. So both of them use something like f of x2 minus f of x1 over x2 minus x1. Both of them use 2 points. So the big difference between the two things is just where are the 2 points. For average, the 2 points could be any 2 points. And those points will always be given to you. So we might say x equals 5 and x equals 11. Right? That's what we said in the last problem. Those are the 2 points. For instant rate of change, we have to find the 2 points because they'll give you 1 point. And you need to make the second point 1 moment before or after. Your choices before or after might depend on the story. If it's a falling object, maybe you want the moment right before it hits the ground. If you're investigating stock prices and you want to know if it's going to rise or fall, maybe you want the moment right after right now because you're looking at the future trend. That's up to you, but our idea of a moment is still 0.001. So if they give you x equals 7, then your other point is going to be either 6.999 or 7.001. If they give you x equals 0, this is like that very last oil spill problem, those of you that did that with us in class, then your two other x's could be either x equals negative 0.001 for the moment before or positive 0.001 for the moment after. So they give you 1 point and you have to find the other point. Then, just like with average, with an instantaneous, you finally do your calculation with a difference quotient. So this question is actually what I think is one of the most important ideas in the whole unit. How is the rate of change, average and instantaneous, how are they represented on a graph? And the big idea is that they're actually both represented kind of by the same thing, and that thing is a slope. Both average and instant rate of change are slope. What kind of things have slope? Lines have slope. So average rate of change, we already said average rate of change requires 2 points. So say the problem gave us 2 points like this. Average rate of change is a slope of the line connecting those 2 points. And we call that line, that's kind of our version of connecting for today, a secant line. And the slope of that secant line is the average rate of change. For instant rate of change, like we said, they're only going to give us 1 point. Let's make a point down here. Since it's only 1 point, although we secretly use 2 points to calculate it, they're so close together we can't even tell. Like the second point would be inside of this dot right here. So the instant rate of change is represented by the slope of a tangent line that touches this curve in more or less just one point near here. It is allowed to touch the curve, it is allowed to touch the curve at other places. If this curve were to continue off down and the line touched it again, that would be okay. But right around here, it touches it at one point, and this line we said is called a tangent. And the slope of the tangent is the instant rate of change. And when you calculate it, we use the word approximate, but if we're just talking about this in terms of a graph, you're allowed to just say that the slope of the tangent is exactly the instant rate of change. So this is the picture that I really want you to have. There's a really nice Desmos Applet where you can kind of move lines and points around. I'm going to put a link to that in the video description so that you can check it out, because I think if you're having a hard time with the picture, it's nice to have something that you can really kind of mess around and feel. So please check that out if you're still not quite sure what the difference is between tangents and secant lines and how they relate to changes. This is a really important question too, and the way it's written makes it seem a lot harder than it is. Identify where the instantaneous rate of change is positive, negative, and 0 on the given graph of f of x. So here's a graph, and they're really just asking us to tell us where the function is increasing, decreasing, or where it has a minimum or maximum. So it's actually the best to start with 0. When the instant rate of change is 0, we said the instant rate of change is the slope of a tangent line. So here's a point, switch colors. Here's a point where the slope of the tangent line would be 0, right? Because there's a tangent line, it's kind of equally balanced. It's sort of like a seesaw or a teeter-totter. Here's another point where it's 0. And here's the third point where the instant rate of change is 0. And notice that all of these points are kind of special because they are minima or maxima of f of x. And maybe sometimes we add the word local minima or local maxima to mean it's not the total lowest point, but just the lowest point around, a peak or a valley. And so if we want to say where those points are, and then we just go to the graph and read them. So one of them happens at x equals -1. We'll go from left to right. So there's -1. Another one happens at x equals 0. And another one happens at, it looks like, x equals 1.5. I like to do the zeros first because if you look at this function, and you kind of imagine a car driving along this function, if you start on the left, as you always do, right now the car is driving up the hill. And it gets to this red point, and then all of a sudden the car is driving down the hill. Maybe a different color for down the hill. The car is driving down the hill until it gets to this other red point. And then all of a sudden the car is driving up the hill. And then, surprise, you get to another red point, and now the car is back to driving down the hill. So the red points tell you where the rate of change changes from positive to negative. The rate of change is positive everywhere the function is increasing. So positive rate of change stands for increasing function. And negative rate of change stands for decreasing function. So the next challenge of this problem is actually to do what it says and write these using intervals. An interval is just an inequality. So I'm going to look at this sort of set of numbers. It's everything, this arrow goes down and like off towards negative infinity. Negative infinity in the x direction, not the y direction. So the x here is more than negative infinity, and it's less than -1. So notice I'm like using this -1 value over here as one endpoint of the interval. But we don't want intervals. All this, like, these symbols are confusing, so we're going to write this as just the interval negative infinity up to -1. The reason I'm using these parentheses here is because positive is not 0. So if I wanted to include 0, I would need to use a bracket instead, all these red points. I'm trying to exclude the red points, so I'm using parentheses instead. The next interval is from 0 here up to 1.5, so I'll say 0, 1.5. If the interval notation is still a little hazy to you, please just look it up on the internet. I don't always trust the internet, but everyone uses interval notation. It's almost always the same. This is something that's really, really standard. You've seen it before in Math 1 or Math 2. And you need to report your answers in interval notation if at all possible. For the decreasing intervals, it's decreasing on the green. So it's decreasing from -1 to 0, and it's decreasing from 1.5 all the way up to positive infinity. Notice that in the intervals, positive infinity is always on the right because it's a bigger number, and negative infinity is always on the left because it's a small number. That's just one of those sort of quirks about interval notation. I know infinity feels big, but negative infinity is actually really, really small. And now we come to number 9. Number 9 is an example of our dirt problem. D equals RT. Distance equals rate times time. So we say solve this algebraically, not with an in-out table, and that's true, but we are going to make a table for this problem because there's 2 characters and a lot of information. So we have Ellie, and we have this other player who is apparently nameless. Ellie is going 3 meters per second. The other player is going 4 meters per second. Ellie is going to be traveling. It doesn't say how long Ellie's traveling because it's asking how long. That's the question. So we'll just say that Ellie is traveling for X seconds. Fine. Good. We also don't know how long the other player is traveling. You're not allowed in this problem to make up another variable. Like, you can't say she's going for Y seconds. It doesn't help. You also can't just say she's going for X seconds because they're going for different amounts of time. So we need to look at this player, and it says 2 seconds later. So if the other player is observing Ellie at a later time, that means that as she starts going towards the puck, she's going for less time. So this other player, the amount of time they're traveling can be expressed with the expression X minus 2. All right. That's all the information from the story. They don't tell us how far away the goal is, and that seems like, well, maybe we're stuck, except we know Ellie's speed, and we know that her time, at least, isn't in a variable. So she's going for 3x meters, and this other player is going for 4 times the whole quantity, x minus 2 meters. By the way, not putting these in parentheses was the biggest error on the whole quiz. Missing the parentheses here, it changes your algebra in a way that you really don't want, but x minus 2 is the entire time. So you have to put those in parentheses if you're doing some kind of expression for a time. All right, and we know that they're going to catch up means equal distance. That's what the word catch up means when you see that in a problem. So then let's just set this up. 3x is the distance for Ellie. 4x minus 2 is the distance for the other player. 3x equals 4x minus 8. Remember to distribute. That's why the parentheses were so important. So then we're going to have 8, adding 8, and that's going to equal 1x, subtracting 3x from both sides. 8 equals x is the algebraic answer, but it's not the answer to the problem. We need to go back to the story. It says, how long will it take the second player to catch up to Ellie? So in that sentence, the second player is the subject. Channeling our English teacher roots here. The subject of the sentence is the second player. So the second player, if Ellie's going for 8 seconds, is only going for 6 seconds. So x is 8, I agree. But the answer here is 6 seconds for the other player to catch up. And while we're channeling our English teacher roots here, we might as well turn this into a full sentence and say something like, it will take 6 seconds for the other player to catch up. That's what a full, complete, clear answer to a problem like this looks like. You have information in a table, you have some algebra, and then you interpret the algebra and tell us what it means. just out of curiosity, I wanted to know how far had all of these players gone. Well, if you want to know how far all these other players have gone, you know that x is now 8, so you could plug a 3 for x over here and get 3 times 8 is 24 meters. So once you have one variable, you can go back to the table and kind of answer any question that involves the story, but you still have to be clear what the question's meaning. Number 10, we have a story and a graph, and it's asking us about speed time and distance time. So I'm going to draw these on the same set of axes using two different colors, one for distance and one for speed. I'm choosing to do this because the times are going to be the same. It's going to help us correlate the actions to what's going on. So I'm going to always do distance first, and then we'll talk about the speed. So Ethan is mad at his parents, and he runs away from home at a constant speed on flat ground. So if he's running at a constant speed, then well, actually, let's do speed first. I lied, because the story starts with speed. So he's running at a constant speed. That means his speed is going to be constant. When he's running at a constant flat speed, that means his distance is going to increase at a linear rate as well. So that's the first part of the story. Let's label the parts of the story. So at constant speed on flat ground, that's 1. So we'll label this part of the story 1. As Ethan runs, he gets a little bit tired, so his speed decreases gradually. Eventually, he stops for 5 minutes. So when Ethan stopped, his speed will be 0. His speed is going to decrease gradually, and maybe he starts running out okay, and then he really, really gets tired kind of on a curve, right? I wanted to have something curvy here until he really slows down, starts to slow down really fast until his speed is 0. So as his speed decreases gradually, he's still running away from home, which means his distance is still increasing, but it's increasing less and less. It starts out going about the same speed, but then his distance really kind of tapers off as Ethan slows down. All right, and so we'll call that part 2 of the story. Now part 3 of the story. Ethan loves Mountain Dew, so he's going to drink his Mountain Dew. While he's drinking his Mountain Dew, other than vibrating a little bit, he has no speed, so we're going to draw a straight line on the ground, a straight line on the x-axis of the graph to represent that he's drinking his Mountain Dew. And during that time, he's not changing his distance because he's not changing his speed, so that part of the graph will be constant as well. But notice that his distance just stays at the same place. His speed has dropped to 0. All right, having drunk his Mountain Dew, he accelerates and runs constantly at an even faster speed for a while. So he can't just instantly go from no speed to some speed. So he accelerates. Whooshoo! That's a fun sound. And then once he's done accelerating, actually maybe it's kind of a smooth curve. It accelerates up, whoa, and then starts to even out at an even faster speed than before. And he runs at a constant speed for a while. Eventually, so let's talk about the distance. The distance here continues to go up a little bit at first. And then once he's going at a constant faster speed, what's important is that he's going to have a straight line again, but it's going to be a steeper straight line than before. We're going to go our graph all the way through the math problem, all the way up here. He's going really, really fast. He's increasing a lot of distance. I guess I should have planned this out a little bit better. I think we can understand what's going on, though. That was part 4 of the graph, so we'll label this part 4 of the graph. I guess this was part 3 of the graph right here. Eventually, Ethan regrets his choices and decides to return home. He turns around and walks all the way home, going the same speed the entire time. So his speed remains the same the entire time, and it says he walks, not runs. So we're going to kind of put his speed a little bit between his original running speed and his speed of 0. And he walks home. It's probably going to take him a long time to walk home because look at all this distance he's gone. So he's going to walk home for kind of a while until eventually he's at home. We're going to really zoom out here. And then once he's at home, maybe you might want to say his speed drops to 0 as he sits and gets lectured by his parents. Sorry, Ethan. It's true. as he walks home at a constant speed, his distance decreases because he's going towards home, and because he's going on a flat line, his distance will also decrease, and once he gets home, his distance will be 0. And then, while he's at home, his distance and his speed are all 0 while he's sitting there getting in trouble. So I hope you've enjoyed this lovely story about Ethan. Your graphs will obviously be a little bit different. It's a little awkward to put them on the same axes, but I think it helps to match all the times up. You can also do the numbers and match the times up. You need to know the difference between a speed time and a distance time graph and what each means and like what different slopes and different pieces of those graphs mean. Here's 2 problems at the very end of the sheet that are kind of puzzles. So they're word puzzles and graph puzzles. The first step is understanding what the words are asking you to do. Draw a graph that has 2 x values where f of x equals 0. So f of x is just like where y is 0. So that's saying like the line is at the x-axis. So I think the easiest thing to do there is just put 2 points right here. And then it says, and 3 x values where the instantaneous rate of change is 0. And we already talked about this. This is true wherever the tangent line is going to have a 0 slope. So this is going to be a min or a max of the function. So now we get to be a little bit creative. Our function's only allowed to like cross the axis twice, but it's got to have 3 minima and 3 minimum or maximum. So if we can only have 3 minima or 3 maxima, then maybe we want to try this. We want to try to come through here, turn around, there's 1, turn around again, there's 2, we'll dip a little lower just because, there's 3, and then back through. Oh, we'll just move that, we'll make a really big point right there. I think that kind of gets the point across. So here's my 2 places where f of x equals 0, boom, boom. And here are my 3 places where the instantaneous rate of change is 0. 1, 2, 3. This problem is also kind of like the last one, but it's giving us just 2 clues about the average or instantaneous rate of change. On a sheet that gave out in class, I did not use the right words. That is entirely my fault. So you should replace that with the word instantaneous. And I already replaced this other one. If we ask this question with average, it's literally impossible because there's infinitely like too many functions that you could draw. But when you have the 2 intervals with the instantaneous rate of change positive, remember that instantaneous rate of change positive meant the function was increasing. And instantaneous rate of change negative meant the function was decreasing. So we need some places where the function is increasing and some places where the function is decreasing. Well, here's our function. We said we need to have 2 intervals where it's increasing. We need to have 3 intervals where it's decreasing. So it sounds like I should start with a decreasing interval and get it out of the way. So it doesn't say how many times it has to cross the axis. That's kind of nice. Let's just draw an interval where it's decreasing. So there's a decreasing interval. 1. Now I'm going to switch to an increasing interval. I like a little one. I like a little interval. There's our first increasing interval. Then we'll have another decreasing interval. So that's 2. Then how about an increasing interval? Let's increase a lot. Because. And then finally another decreasing interval. Something like that. This would be an acceptable answer to this question. Maybe a little bit dubious right around here about increasing, decreasing, but I think in general that's what we're asking you to do is correlate when we say instant rate of change positive. That's all these places where the function is increasing, and instant rate of change negative is all the places where the function is decreasing. So that's kind of the way that we would approach this last question. It goes back to the idea of graphical interpretation and function analysis. The hard part here is not drawing the function, it's understanding what the question wants you to do on both of these questions. So just in that spirit, know the words. So that's it. That's the end of the review sheet. If you can do all these questions, I think you're going to be just fine on the test. If you're not sure about something I've said, try to watch the video again, or please just send me an email. I am happy to clarify stuff. But, you know, the more you practice, the more you work, the more you're sure you really understand everything that we just did, the better you're going to do on the test. I don't want to end today without showing you a picture of a cat. I feel like that's kind of part of the bargain here. But you can't make a cat be on a video. That's just not how cats work. So here's a picture of Pepper. She is sitting on my bed right now. This is her. She's not happy. And have a happy Sunday. I will see you all tomorrow.